Assalamualaikum everyone. In today's video we are going to solve this problem. Okay, you see that this is a beam and then there is a moment applied here in clockwise direction, then we have a point load and then there is a distributed load. Okay, and that's a roller support. So that's a cantilever overhanging beam. Okay, elastic modulus is 200 GPa, which is basically the structural steel, and second moment of area is given, second moment of inertia. So if I assume that the cross section is square, then solving that, okay, breadth and height are equal, so you will find that the cross section dimension would be 221.336 length and breadth. Okay, so I will use these dimensions, basically this equal to this one, to determine the cross section. So let's move to that. Okay, first of all, engineering data, we see that. So if you double click that, then this is the Young's modulus, which is basically in Pascal. So if I change that to GPa, so you see that this is 200 GPa, which is exactly the given. And then okay, just leave as it is. And then if you double click that, then the design modeler will open. Right now, click the just XY plane, look at, and then draw a line. But let me check that. Okay, it is the dimensions of the beams are 4, 6, 4 and 8 mm. Okay, so I would create that in line segment because I need these nodes, okay, where these two elements basically intersect or meet. So I would define so that I can take this point as a node and I can apply load. So just create I would not so not to create a single line, so just segments of 4 meter, 6 meter, 4 and 8. So that's what we will do. Units are in meters, so just leave as it is. So just select the line and then make sure that if you see the H, okay, then it means line is horizontal. It may seem that the line is not to you, that line is not horizontal, but as long as you see there is H written here, so if you click here, the line would automatically become horizontal. So just again making sure that these lines are coincident, and there is a P. So P written there, then this is the second line segment, and then this is the third line segment, and then I have the fourth line segment. Okay, so now I have to define the dimensions. Go to the dimensions, general. Okay, so you see that this is H1, this is H2, this is H3 and this is H4. So let me 4, 6, 4, 8. So that's 4, and then second one is 6, 4, 8. Okay, so you know that this is basically a line, and we cannot perform an analysis on a line, so we need to convert that into this sketch into line body. So for that, go to the concept, select lines from sketches, and then select this sketch. So I can select it from here and then apply. You see that? And then okay, so this one is created, but I need to generate it. So I have a line body, but I need to define the cross section as well. So for that, go to the concept again, cross section, and then I would select the rectangular cross section, and what I need to define the dimension, what is that, 221.336. so for that, just let me change the unit here, 221.336 here, and then again 221.36 here. Okay, that's easy to define. I don't need to change that. No, that's fine. Okay, so I have defined, and from the again select the line body, and then here select the cross section. Okay, so now my geometry is complete. So to see that, I can just click cross section solid. You see that? Okay, so just using the right mouse button, I can zoom the area and I can see that, and using the middle mouse button and control key, I can pan my object. So that's fine. Okay, this is all okay. So this is fine, just close it, and then just open the model, ANSYS mechanical. So it will take some time, just wait that. Okay, ANSYS mechanical. Okay, just it takes some time. Now just look at that. I have to define a point load. I have to define a fixed support here and a roller support here, a distributed load, and there is a point load and a an applied moment here. So for that, just okay, this is ANSYS mechanical. Okay, that's fine. Okay, first of all, let's check that. Okay, I have my geometry and I have a line body, and in the line body the assigned material is structural steel, which is fine. And then structural steel, these are the properties of the structural steel. Okay, before creating the mesh, okay, this is the cross section and area. I can change the dimensions of the cross section from here as well. Let's see if I want to change, then that can also be changed from here, right? So 221.336. okay, that's the problem. Okay, this is 336, so I can change it from here. Okay, that was 336. And then okay, where's my geometry? You see that, just let me reset the layout. Okay, so this is my geometry here. So I want the view perpendicular to x-axis, so just okay, not sorry, z-axis. Okay, so this is the z-axis, xy, so that's fine. So I can change the view from here as well, from the triad. Now let's see that I can apply the boundary conditions here. So let's see that I have to apply a fixed support here and the roller support here. So for that, what I need to do, go to the static structure, right click, and then select the fixed support. Where is that? And then select this node. Okay, make sure that this vertex filter is selected, and then select this node, apply, and then I need to, this is the second one and this is the third one. At this point I need to, how much? Okay, there's a roller support here, so right click, insert, and then I can define the displacement condition. Okay, for the displacement condition, you see that this is a line body, so there is no need to restrict the displacement in z direction. So I need it will restrict the displacement in the y direction. So horizontal movement is allowed, but the vertical movement is not allowed. So any movement in x direction is allowed, so that I would keep that free. And for the y direction, okay, I would restrict that 0. Okay, that's constraint. It's default. You can also for the z, you can just left it free as it is, or you can also fix it as well. Okay, because that will not create a problem because that's a line body, and obviously so there will be no z direction movement. So I would just okay, just define that 0 as well. Okay, that's also fine. Okay, so now for the next one, I have to define a 20 kilonewton load for that at that node. So this is the node here, apply, and what I need to apply, select here, insert. I don't need to define this displacement condition here, so just insert, select, insert, and the force. Okay, that's what I wanted to make sure that. Okay, I think I have changed the node. Okay, that's it was not this one, so I need to change it to again, where is that? Let me select that using the box selection. Okay, this one. Okay, so just change that. I accidentally changed that to this one. Okay, so that's fine. Okay, so for the force one, I need to select this node, okay, and apply. And how much force? I can use the component option. So minus 20,000 kilonewton, so in y direction, so minus 20,000 kilonewton. So that's the force defined in the y direction, and that's a static loading here. You see that from a time scale 0 to 1, so it will gradually apply the load. At time 0, the force will be 0. So as it will increase from 0 to 1, okay, so it will the force will gradually increase. Okay, so that's a linear pattern, you see that. And then at the same node, okay, I need to define I need to add the moment as well. So if you right click that and moment, and then again select this node, apply, and for that I would select the component. So I need to define the moment in z direction. Okay, because that's perpendicular, that's the perpendicular axis, but the moment is clockwise. Okay, so clockwise means I need to define the value in you see that negative negative value here. So it's the z component here, so that should be minus 5,000. you see a minus 5000 Newton millimeter, so which is equivalent to 5 kilonewton per meter. Or I need to change the unit here, so I would prefer the meter here so that I can see. So that's minus 5 Newton meter, that's wrong, so just change again that to minus 5000. okay, 5 kilonewton. okay, see there, just check it's clockwise about the z-axis, okay, as indicated here, so that's fine. Next I need to apply this distributed load here, so that's 5 kilonewton per meter between the node 4 and 5. So for that, basically just select the line and then select the line pressure here. okay, this is the line of, so it basically exerts the distributive force per unit length. So just select the line pressure here. You can see that the units are Newton per meter, so which is basically here Newton per meter. So I need to select this edge, so I will select this edge. okay, this edge, apply. So this edge is selected, and for the vector, okay, this will remain vector, okay, or I can define that by the component. okay, that's fine. And that's minus 5000 in y direction. okay, you see that. okay, this is the y direction, minus 5 kilonewton per meter, which is exactly here. So I have defined all these conditions. okay, so let me check that. There's a fixed port here, there's a displacement condition here, and then at this point there is a force and the moment, and then we have the line pressure. okay, all these are defined. okay, that's exactly what I wanted to do. okay, next thing is I basically want to draw the shear force in the bending moment diagram. So how I can do that? okay, so let me just first solve the model here. okay, oh sorry, I need to generate the mesh. This is what I have forgot. okay, but ANSYS will automatically create the mesh then. okay, let's see, just wait. okay, so it have solved the automatically defined the mesh. okay, just let me check that. okay, there are some units. okay, I can control them, but just let me keep that, or I can define the element size as well. okay, so just go with the flow. okay, just keep it as it is, or you can define the size here. so I will go with that, that's fine. okay, first of all I need the shear force and the bending moment diagram. so if you go there, right click, beam results, so there is this shear force here. so if I click here, the total shear force, I don't need the total shear force, I basically need the directional shear force. okay, the shear force in a particular direction, and online bodies, which is fine. okay, but let me show you one thing. okay, if I generate the shear force, I mean evaluate all the results, so it will calculate the shear force, but it will not create the graph. okay, how the shear force is varying. okay, you would see that. okay, this is the maximum force here, and you can see the values here, but you will not get the shear force diagram, which exactly I wanted that. So to get the shear force diagram, okay, what I need to do? okay, I need to create the path here. So for that, okay, just let me just clear the generated data here, and I need to define the path here. So go to the model, insert, right click, insert, and then select the construction geometry, and then select the path. okay, then I need to define the path along this line. okay, so path type is 2 points, so I can select the start point and the end point, but there is another option here, which is basically the edge. okay, so I can select an edge. okay, so and then I can define the path along that edge. But right now, okay, I will select this hole. okay, so I will select the box selection here, so that I can select all the edges here. so I have selected them, and then apply. okay, so I have selected all the edges, and then I have defined the path along that path. okay, so you see that. okay, now I have created that, right click, and then again beam results, so the shear force, but I need the shear force in the y direction. okay, so just in the scoping method, just change to the path, select the path here, and then from the total shear force, change that to directional shear force in the y axis, which is fine, and then solve it. Okay, just wait a second. Okay, now you see that, okay, this is shear force 2. Now you can see that this is the shear force diagram. Okay, it shows me these are the values. Okay, at 0 meter, what is the value of the shear force, and I can export that data. Just right click here and then you can export that, or you can just right click here and then export, and then export text file. Let me get that to shear force values and then just save it. Okay, so just wait a second. Okay, then Excel file, you see that, okay, with the distance, okay, 0 meter, 1 meter, okay, till 22 meters, okay, these are the shear force values, okay, or these are the coordinates, x and y coordinates of each of these nodes, which is fine. So this is how you can export that data, or you can export the animation as well. And next thing, okay, just let me delete this one. I don't need this. I need the shear force and the bending moment diagram. So I got the shear force. For the bending moment, right click, insert, and select the bending moment here, and the scoping method, change that to the path, and then select the path here and total bending moment to the directional bending moment, and then evaluate all the results. So now you see that this is the bending moment diagram, okay, and these are the bending moment values. Okay, so now you know that how you get the shear force and the bending moment diagram. And if you want these two diagrams into your report, okay, then you can just go to the results, and then in the image, okay, just select this one, and then you can add the chart here, and then just call it, rename it to the shear force diagram. And for the bending moment, just select here, and then again select this bending moment chart, and then it would create the bending moment diagram. Okay, that's also fine. Okay, next is I need to calculate the nodal displacements. Okay, I need to find out what's the displacement value at 0.1, 2, 3, 4, and 5. Okay, these are the nodes here. So if you go there, okay, first of all, I need to get those nodes. Okay, these are the nodes. So for that, how I can do that? Okay, because I need to define, I cannot define the path along that nodes. So I need to basically, similar to that, I have created the path. I have to create a name section, okay, which basically address those nodes. Okay, so how I can do that? Okay, so right now you see that if I select the vertex here and the box selection here, and then okay, these are the nodes I'm interested in, but I don't know the you see that I don't know the node ID. Okay, because you see that if you go to mesh, and then you see that go to the statistics, and you see that there are 45 nodes here. Okay, and I need what I wanted to create, I need the nodal displacements for these nodes only. So first I need the node IDs. Okay, so if you just click here, so 5 vertices are selected. Okay, so vertex 1, vertex 2, and all the coordinates of all these vertices are given here. But how can I get their mesh ID? I need the node ID for that. So if you go to the mesh here, and then selection, go to the selection, and this is the mesh ID here. So okay, so I can create the selection for these nodes, but I need the node IDs, which exactly I don't see here. So I need, how I can see that, okay, these are the node numbers. Okay, which one, right now it shows that 45 nodes have been created and there are 22 elements, but this is node number what? 1, 2, 3, 4. Okay, we know that these are created in somehow random fashion. So for that, you go to the display. Okay, if you don't see that, if you see the numbers, that's fine, but if you don't see the numbers, just go to the display, select the preferences here, and then you see that there is the option of node numbers, okay, or the node IDs. So just click here and then apply changes. Okay, so now you see that now you can have these numbers. Okay, so just note down the nodes ID. This is the 20, 21, 10, 1, and 2. Okay, so now I would define, I would catch these nodes. Okay, so mesh ID, so just write numbers of these nodes here: 20, 14, and then 10, 1, and then 2. Okay, so and then create named section selection. Okay, so ANSYS will create a name selection here. Where is that? Okay, this is okay. And then you see that these are 5 nodes which have been selected here, and these are the node IDs. Okay, and then 20, 14, 10. Okay, these are now visible. Now I can determine the nodal displacement along these values. So for that, again, right click, insert deformation, directional deformation, and displacement in y direction. And in the scoping method, I would select the name selection, which is basically what my selection. Okay, or I can just change that to rename that to nodes, nodal nodes, my nodes, or I can just say that my nodes. Okay, that's fine. Just say it to my nodes, and if you go that, you see that my nodes. Okay, name selection here is the same. Okay, from the orientation, change that to y direction, and then I have this directional deformation. Right click and evaluate all results. Okay, so you see that these meters, these are in meters. I can change that to millimeters, so that the values are, you see that the maximum, the minimum is 15.588 and the maximum is 534 displacement. Okay, I see that here, or you can see that, or I can get the maximum or minimum from here as well. The maximum, okay, the maximum is here, means 15.52. okay, which is basically the positive, it's the negative. You see that the minimum in around about 532 is here, or you can just get the probe here, or what is that? Okay, and then you can evaluate that, but it's not working. Just leave it. Okay, next is what I need to okay, so how to apply moment. You know that, calculate nodal displacement, shear force and bending moment diagram, draw, export data. But there is one thing else which is basically I'm forgetting. Okay, so to check the results, I can also add the support reactions here. I need to determine the reactions to go to the probe here, and the force reaction and the moment reaction, which is basically at the fixed port, you know that. So for the force reaction, just change that name to for the fixed port. Okay, I would change that force at fixed support. Okay, which is fine. And then okay, so just like the fixed port here, this is fine. And then next I need another moment reaction. Yes, I need the moment reaction as well at the fixed port. Okay, which is basically I wanted that, so fixed port, and I need force reaction at the roller support as well. So just like the force reaction, F2, or just the displacement condition, and then change this name to roller reaction. Okay, that's fine. Okay, so I have created that, and just right click, evaluate all the results, and then we will compare our results with the values. Okay, so first go to the directional deformation or the nodal displacement values. Okay, which are exactly this one. Okay, I can export the data here. Just right click, export text file, and then node values. Okay, nodal displacements, just write that. And okay, these are the results from the book. Okay, let's see that. Okay, so you see that the maximum value is 533 and the minimum is 15.588. okay, so our values are in the range. You see that these are it depends upon basically these results have been generated from the MATLAB, so the results also depends upon, you see that the solver as well. So it shows me that at node 1 the displacement is this one, node 2 displacement 534, which is this is the node 2, you see that, and the node 10 is displacement is 0 because there was a roller support here, and then at 20 this is also 0, so which because that's a fixed port. Okay, so these results basically corresponds with the validation. Okay, so it means our results are accurate, approximately accurate. And then we have the moment. Okay, you see that this is the moment about the z-axis, and its minus means it's just clockwise, okay, and it's around about 1 to 1, okay. You can change the units to correspond that, or it's 1 to 1.4 approximately, so 1 to 1.2, so it's Newton millimeter, okay, 10 raised to power 8, so it's approximately the same. And the reaction force, you see that roller reaction force, it's in the y direction 9262, and for the force at fixed port is 326264 here, or 916 there, so that's fine, okay. So that's how we can create the nodal displacements, and we have learned that how to apply, how to create the nodal, how to select the nodes, to apply the moment, and then export data, okay. That's I have shown you. And then to generate the report, just go to the home and then report preview. ANSYS will automatically see what you have done, and then you can and it will generate the report for you, okay. That's fine. That's the basic feature, okay. So I have my report here, and then you see that, okay, just close it, okay. So that's my report, and that's my load application, and you know, the shear force diagram, bending moment diagram, and then these are the results, okay. You should also add the pictures of the boundary condition, I guess. So just close it here. So these are the boundary condition. To add the picture of these boundary conditions, just go to the home, then images, and then figure, and then change the name to boundary conditions, and then you need to add the mesh as well, okay. So you must add this picture as well, okay, the mesh picture, the boundary conditions, and then the results of each category that needs to be displayed. And for a particular value, let's say that the force, or let's say the directional deformation, you might see that the gap may be large, okay. You see that 106 and then 107, okay. If you want to add further in it, then you can just select that, and then you can add your further colors here. That would work, okay. I hope you get that, and I will give you an assignment related to that. I want you to solve a similar assignment from the book, or draw the shear force and the bending moment diagram, and then any problem we can discuss in the class. Thank you.